Hi students, I'm going to do a little video here on some calculations that have to do with Dalton's law of partial pressures. Right before this, there's a really good video that I got from YouTube that explains Dalton's law of partial pressure. It almost follows exactly my packet pages here. We're on packet page 93 right now. And so I'm not going to go over this because it's in that video. So I'm just kind of show you where we are. So what happens is that when we have this Dalton's law of partial pressures, we end up with a few equations. Here's one, here's another one. Turn the page for a second. Here's another one. Okay, so I want to summarize all these equations in one place because we're going to need them. And I want to talk a little bit about how to solve problems with Dalton's law of partial pressures. So let's see what we got here. So the first equation there at the top is, the first one is on page 93 there. That is Dalton's law of partial pressure. So briefly, what this is about is that when you have a mixture of gases like air, or anytime you have more than one gas present in a mixture, air is mostly nitrogen, next oxygen, each of those gases in the mixture has its own pressure. The pressure you measure, like with the pressure gauge, is the pressure total of all of them together. It helps to understand that if you realize that the definition of pressure, real quick now, do a little physics here, pressure is force divided by area. And so the force of a gas is just due to all the trillions of particles of gas that are inside the container bouncing around and hitting the side of the container, hitting the pressure gauge, and that creates a force. The over area means you're measuring that force, not the total force in the whole container, but only on a part of it. So an example of this that we don't talk about in chemistry, I'm not going to quiz you on, is the pressure unit PSI that we use in the United States a lot for tires and bicycle tires and stuff. That stands for pounds per square inch. Pounds is the unit for pound is lbs per square inch. So here we have it as its real units, pounds over square inches. This is abbreviation, pounds per square inch. Pounds is a unit of force, okay, and per square inch. So it's telling us if we were to draw a square that was 1 inch, it's a bad square, but let's pretend that's a square. It was 1 inch wide by 1 inch long, then you would have a 1 inch square area. 1 square inch. And the pressure exerted by the gas that's colliding with that is what the pressure is, okay? And if it was pounds per square inch. Now, we don't use that unit too much in chemistry, but it gives you an idea. So the reason why I bring that up now is because in Dalton's law of partial pressure, if you have a mixture of gases, they're all going to be exerting different forces because because there's usually different numbers of moles of each one. Now, there could be the same. You could have 1 mole of each, and then they'd all have the same pressure. But usually, you have different number of moles of nitrogen, of oxygen, of CO2. The more moles you have of that, the more particles there are, the more collisions that gas makes, and the more its individual pressure. So pressure is due to collisions. The more particles, the more collisions, and therefore the higher the pressure. Each individual gas has its own pressure because it has its own number of collisions. So we measure the pressure total generally. Okay, so this is Dalton's law of partial pressures. That's one equation. The next one that you need to keep handy is, oops, sorry about that, is that when we're using the ideal gas law, if we have a gas mixture, the pressure total times the volume equals the moles total RT. So that's just your ideal gas law. PV equals nRT, but here we're specifying we have a mixture and we're looking at the total pressure and the total number of moles, which is counting particles of the gas. Also, each individual gas will have its own ideal gas law. We're using gas A here, but it could have been B or C. They will all follow the ideal gas law individually. So the pressure, we call this the partial pressure of A times the volume equals the moles of A RT. Now you notice there's no volume of A here. Took me a little while as a student to remember that. That's because the volume of a gas is the volume of the container it's in. even if it's a mixture, let's say all these dots, some of them represent oxygen, some of them represent nitrogen. They all have a volume of 2 liters, even though you only maybe it's 78% nitrogen and 22% oxygen and only 1% carbon dioxide. They all have the same volume. So the volume is of the container that the mixture is in. So for example, if this was our mixture here, A, B, and C, and the pressure total here, and this was A was part of this total, this V would be the same. And of course, so would this T. And that leads us to the next equation, which was derived in that video. I'm not going to show you the derivation again. But if you take these equations and divide them, you get the pressure A over pressure total is equal to moles A over moles total. So don't look at this part. Just look at that. Right. So what this tells us is that the fraction of the pressure, so the pressure of one gas over the total pressure, is equal to its moles divided by the total moles. This is a very handy little ratio to have. Can solve a lot of problems quickly, because if you know 3 of these, you automatically can calculate the 4th one, so you need to keep that one in mind. Now this guy here, moles A over moles total, has a name, and it's called the mole fraction. And kind of obvious why, because it's a fraction. So let's say there was, out of this, let's say we have 10 moles total. Let's say A is 3 moles of that 10. Then this would be 3 divided by 10. So it's the fraction of the moles that belongs to A. This is telling us the mole fraction is equal to the pressure fraction because they're proportional. Now mole fraction has a symbol. It's this guy, chi sub A. Mole fraction is not just for gases. You can have mole fraction in mixtures of liquids or solids. It's just the mole fraction, it's taking the moles divided by the mole total. But only in gases does the mole fraction also equal the pressure fraction. So you need to know all parts of this. You need to know that the mole fraction is equal to this quantity here, because I could ask you to calculate a mole fraction. You need to know that the mole fraction can be also determined from a pressure fraction, so that this is equal to this. And you need to know it without even paying attention to that symbol. You need that too. So all those will help you in doing some of these problems. Okay, so I just want to have that handy because we might need that. So we're going to look at a problem down here that is given on the bottom of page 94. I'm going to just move that up here, okay? And it says a 1 liter sample of dry air at 786 torr and 25 degrees Celsius contains 0.925 grams of nitrogen plus other gases, oxygen, argon, carbon dioxide. What is the partial pressure of nitrogen and what is the mole fraction of nitrogen? Okay, so we're looking for partial pressure, we're looking for mole fraction. So let's start with A. What is the partial pressure of nitrogen? I'm going to bring my equations back here a second. So partial pressure of nitrogen, this has partial pressures in it, but this equation won't help us because we don't know anything about the pressure of other gases. We don't have, they didn't give us the pressure total. Could we calculate the, oh, I'm sorry, they did give us the pressure total. Sorry about that. They gave us the total pressure, 786 torr. That's what that is. It's the pressure of all the air. But we are looking for the pressure of nitrogen, but because we don't know the other pressures, we can't find nitrogen from this equation. How about from this equation? Pressure, if A is nitrogen, pressure of A, volume, moles of A, RT. Well, let's see what we got. We would need a let's say we use this to find the pressure of nitrogen. What else would we need? We would need a volume, we'd need the moles of nitrogen, and we would need the temperature because R is constant. So do we have those? Do we have a volume, moles, and temperature? So we have a volume because we have a liters, okay? We have, that's a total pressure. We don't need that for this equation. We've got a temperature, and we have grams of nitrogen, but grams can go to moles. So we have all the things we need to use this equation. We have moles, which we can get that from grams. We have a temperature, we have a volume, so we can use the equation to calculate pressure of nitrogen. So this is a good equation for us to use. Now, we also have another equation down here where we could calculate a partial pressure. we have a total pressure, so we could use that. We can calculate the moles of nitrogen. Do we have moles total? If you look back at the equation. So I'm trying to see, this one for sure we can use. Can we use this one? So let's go here. Do we have moles total? Well, we don't. Turns out we can find the moles total if we wanted to. Why? Because we have the 1 liter, which is the volume. We have a total pressure and we have a temperature. We could use this equation to find moles total and then use this equation here. But that's a lot of steps. So there's 2 ways to do this problem. I'm going to use the faster way, okay? But that's a good thing to keep in mind because sometimes you have to do the long way, okay? This one, we have all the information we need. We can do the faster way, which is to just use this equation here, okay? So the first thing we're going to need, and that's what's done here, is we need to change those grams of nitrogen to moles. So this is for nitrogen, 0.925 grams of nitrogen. This is the molar mass of nitrogen in 1 mole. This is the moles of nitrogen. So this is now moles of nitrogen. So that is moles of nitrogen. Okay. Now we're going to go to our equation, which says pressure is equal to pressure of nitrogen volume equals moles RT. And I'm going to solve for pressure. So if I do that over here on the side, pressure of nitrogen equals moles of nitrogen RT over V. So everyone see how I got that, right? Just took this equation here, that one right there with the arrow, and I solved, oops, sorry, I wanted a nitrogen here. And I solved for pressure, and I substituted in the formula for nitrogen for A, okay? So now we can use that equation to solve the problem, this part of the problem, part A, which is what is the partial pressure of nitrogen. So I got my moles of nitrogen here. I just calculated that right here. I got my R, my friend R here, right there. My temperature, I got to put it in Kelvin. Here's my Kelvin, 25 degrees Celsius, 298 Kelvin. I got 298.15 because I added 273.15. Technically, I only got that many sig figs. I'm going to use the whole thing for calculating, but keep in mind that's only 3 sig figs there. And my volume was given as 1 liter. So if you do this in the calculator, you'll see your liters cancel, your Kelvin cancels, your moles cancel. You're only left with these atmospheres, and that comes out to 0.808 atmospheres, and that's the partial pressure of nitrogen. So that would be the answer to part A. Okay. Now, why am I doing this stuff down here? Well, because there's a part B. And the B says, what is the mole fraction of nitrogen? So mole fraction, we said, there's really 2 ways to figure that out. We said that mole fraction of nitrogen would be, the definition would be moles of nitrogen over moles total. So we could, if we had those 2 quantities, we could get mole fraction. We already have moles of nitrogen. Could we get moles total? We don't have it, but could we get it? Well, we could if we go to this equation, pressure total volume equals moles total RT. We have the pressure total that's given to us. We have the volume, we have the temperature. So we could calculate moles total here. That would be an option. And if we have the moles total, then we could just plop it right in here and we're done. So that's one way to do the problem. I did it a different way. And that is to say that this is also equal to pressure of nitrogen over pressure total. Why did I do that way? Because it's going to be faster. So I'm going to ignore this. I don't even need that. Okay. Mole fraction is also equal to the pressure of nitrogen over the pressure total. I have the pressure of nitrogen right here. Okay. And I have the pressure total right here because this is the pressure of the air, which is the mixture. So I already have those 2. So I can just put it here, but there's a little problem. They're different units. This is the pressure in atmospheres. This is the pressure in total pressure in torr. So this is my pressure total, but it's in torr. I've got to convert one to the other because I got to have them in the same units so I cancel, because this whole mole fraction has to have no units on it. I could have done either way. I could have changed this to atmospheres so that it matches with this one. Or what I chose to do is, since this was sitting right in my calculator, I'm just going to change that to torr. So I took that number, said 1 ATM is 760 torr, but I only have 0.808 atmospheres, so I have 614 torr. So that's also the partial pressure nitrogen, just two different units. So which one is the answer to A? Either one, because I didn't specify a unit. If you were doing this on a test or a quiz, you'd have to, if it was multiple choice, you'd have to make sure your units matched. Otherwise, if you were just writing it out, either of those would have been fine, because I didn't specify a unit. So, but now we got the pressure of nitrogen. So now I'm going to take that pressure. Now we're going to use this, right? So the pressure of nitrogen, 614, divided by the pressure total given is my mole fraction, because that's also equal to, the mole fraction, and so is that. And so that comes out to 0.782. So that's my mole fraction of nitrogen. What does that tell us? Well, you can always change fractions to percents, right? And a percent, that would be 78.2%. So that tells me the 78.2% of the molecules, not of their mass, not how much they weigh, just by counting them in this sample, is nitrogen. So about 78% of the particles are nitrogen. So that's an example of partial pressures. There's two problems there. Now, I want you to try practice question on your own. Try practice question 71 in the practice questions in packet file 4, packet 4. And be careful though, because it looks real similar to this problem, almost asking for similar things, but it's tricky because it's different. You can't solve it the exact way. So I don't want you to look it up. I don't want you to try to Google it right away. You can ask me eventually. Actually, you don't even have to do that. The solutions are there, right? So you can even look up the solutions to those practice questions. They're right at the end of the packet, but struggle with it for a while before you do that. Keeping in mind, it's going to be using some of these equations. Might not be the same ones in the same order, but you're going to use these equations to get there. So see if you can do that problem. Okay, it's an important one to try to be able to do. Okay, so we're going to keep going with this partial pressure stuff. And there's a lot more in the a lot more homework questions. I might do another video, not with this one. I might do another video and do a couple of those examples, because some of them are tricky. But right now I want to finish this here, this packet stuff. So this is the next page. We're on 95 of the packet, and this is an application of partial pressures to a laboratory situation. And I posted a little video about what this is about, and he kind of explained it. So basically what happens is sometimes when you do an experiment, you have a reaction, and the reaction generates a gas. In this case, it's kind of hard to see, but it says zinc and hydrochloric acid. That will generate hydrogen gas. Now let's say hydrogen gas is the reason you're doing this reaction. You want to catch it because you want to do something with it. So how do we catch a gas that we're generating from a reaction? If we just leave this open to the air, it's just going to escape. So a trick that we do is that we take a container and we fill it with water, an open container, like a bottle or a beaker or something like that. And we fill it, usually we do not with a beaker, but something with a flat opening, like a glass bottle. We fill that right side up. This is upside down right now, but we start with it right side up and we fill it with water. And then you cover the lid of it and you turn it upside down and put it in the water. So this is a container of water here, this like pool of water. And what that does is, by filling the container with water, there's no air in the container to start with. So now when you turn it upside down, there's no outside air in there. The only gas that can be up here is going to be mainly the gas you generate. So what happens is then you stick this tube underneath here, and as you generate the gas, the hydrogen in this case, it bubbles up and it starts to fill this, and it starts to push the water that was in here down. So there's atmospheric pressure though on the outside though. So there's atmospheric pressure pushing down on this water, because there's water, kind of hard to see in this picture, but there's water in there. So there's atmospheric pressure that's pushing this down, and that's what's holding this water level up. And then what happens is, as this kind of starts to fill with gas, you get a pretty pure gas on the inside here. And then eventually the reaction stops and you have your container full of gas. Now, the problem is that what it says up here, all right, all liquids have vapor above them. So the word vapor is just another word for gas. But when we use the word vapor in chemistry, we usually mean a gas that was recently a liquid. So think of the word evaporate, right? It has the word vapor in it, evaporate. And so as the liquid evaporates, it goes into the gas phase. And we usually call that the liquid's vapor. And so what happens here is the hydrogen that we collected is in there. That's what these little guys are, these little small molecules. But what's going to happen is if you see this one, let me see if I can zoom in on this a little bit, picture better. Sure I can. There we go. It focuses. One second, still with you. Trying to focus it a little better. Okay, that's about as good as it's going to get. Okay, so what's going to happen here is that the water molecules, see, these are water molecules, and the layer of the liquid layer is like here. So what's happening is the hydrogen that's inside this container, that's these little guys here. See, it's a diatomic. See this little guy here? That's the hydrogen. This little diatomic is being joined by water molecules that are evaporating. So your goal was to catch a gas that you generated here. So you could have that gas, do an experiment on it, do something else with it. But now it's not very 100% pure. It's mixed with this water. So there are ways to get rid of that water. We're not going to worry about that right now. What we're going to be worried about is calculations involving this. So if you wanted to calculate how much hydrogen was generated, what the volume is, you're going to have to take this water into account. That's what this topic is about, collecting gases over water. Let me zoom out a little bit. Okay, so the idea here is that when you have this gas that you've collected, it's now a mixture. It's the gas that you collected, in the case below it's hydrogen, plus some gaseous water, which we call water vapor. So the pressure of that mixture will be equal to the pressure of the gas itself, what you collected, plus the pressure of water vapor. Now, you can't measure those individually though. You can only measure the total pressure, but you can look up, this is called the vapor pressure. So vapor pressure is just a gas pressure. It's just that it's the pressure of the gas that's right above the liquid, and it's the same molecules as the liquid. So it's the partial pressure of those liquid molecules right above it. You can, for water, you can look up the vapor pressure at various temperatures in a reference book, in your textbook, online. So we have compiled this. Vapor pressure depends on temperature. The warmer the liquid is here, the warmer this is, the more of it evaporates. So the more the pressure. If you do this in colder liquid, if this water is colder, you'll have less than you do if you do it in hot. So that's why you have to look up the vapor pressure as a function of temperature. Okay, so all that big explanation, and now we're going to try a problem. Here we go. So this kind of goes by the last picture. A sample of hydrogen gas was collected over water. So when you see that, that's your key. That's your way you know that's this type of a problem. It's going to involve that equation of partial pressure. So a sample of hydrogen gas was collected over water at 22 degrees Celsius. So we know the temperature. And this is a 685 millimeters of mercury. That's a pressure. But if it says it's collected at this pressure, that means they've measured the pressure of the air around it, and therefore it's actually the same as the pressure inside, and that is the pressure total. So the key is, unless they specify it's the pressure of one particular gas, it's the pressure total. Now you might say, well, they said a sample of hydrogen gas, so isn't that the pressure of the hydrogen? No, because the way it's worded, it was collected over water, and this is the atmospheric conditions, temperature and pressure. And therefore that's the pressure, the total pressure inside the container, okay? The volume of the container was, so that's obvious, that's the volume. Calculate the mass of hydrogen collected And now we're told the vapor pressure of water at 22 degrees, which is our temperature. So we have the vapor, we have that. So that's good because we're going to need that in order to do the problem. Okay. So how do we work this? Well, if you look at all this, you say, well, this should look a lot like like a problem, similar to problems you did on the practice, the review quiz 9. If you think about it, PV equals nRT. And if you remember, one of those problems at the end asked you to find mass of a gas. And what you were supposed to do there is say PV over RT equals N, solve for N, and then change that to grams using the molar mass, because this is moles. So we've got a pressure, we've got a temperature, we've got R, we know T. So this is a lot like the ideal gas problems, that easy ones. There is a difference though here, and that is in this regular PV equals nRT, we're not worried about a gas mixture. We're not worried about Dalton's law of partial pressure. So we're going to have to change this a little bit. And that is that if I'm in a mixture, okay, so in a mixture, which I'm in, okay, the moles of hydrogen that I'm trying to have to, because I want grams of hydrogen. The moles of hydrogen I'm trying to calculate, I have to use the pressure of hydrogen in there. I can't use the total pressure. I can't use this. I have to use the pressure of just the hydrogen. The volume's okay, and the temperatures is okay, because that's the container, but the volume of the container, but the pressure has to be just of hydrogen, and I'm given the total. So it's like we have to do a little correction. So we're going to go to the equation, Dalton's law of partial pressure. Pressure total. We only have two gases present, A and B, and I'll put the right ones in there, right? Pressure total, pressure of the hydrogen we collected, plus the pressure of the water vapor, which this is the vapor pressure, where it says here, the vapor pressure. That's the vapor pressure of water, right there. So it's the partial pressure of water that's hanging out over a liquid is called the vapor pressure. So now we have a way to do this, because I've got the pressure total, I've got the vapor pressure of water, and I can find my pressure of hydrogen and then plop it in here. So I'm just going to solve this. So pressure total minus pressure of water equals pressure of hydrogen, okay? My pressure total is 685 millimeters of mercury. Millimeters of mercury and torr are the same thing. My vapor pressure is 19.8, also millimeters of mercury. If for some reason these are not in the same units, okay, like maybe if this is atmospheres and this is millimeters of mercury, this is almost always given in millimeters of mercury. Vapor pressure, almost always. So when you look it up in a table, torr or millimeters of mercury. So if they're not the same units, you got to convert one to the other to make sure they're the same. You notice how this is small. Total pressure is actually kind of low for a total pressure. Usually total pressure is like 700 and something. But that's okay. It's still pretty big compared to this, which is small. It's a small number. It's almost like we're doing a little correction factor. Our total pressure is this. Most of this is going to be due to the hydrogen, but we got a little water mixed in with it, so we're kind of subtracting it off. If you do that, you'll see you get 655.2, and that is millimeters of mercury. Now, the 0.2 is a little extra sig fig, because when you subtract, you count decimal places. So this is to the ones place, this is to the tenths. But I'm going to bring this extra one with me because I'm going to do more calculations. So I always carry extra sig figs with me until the very end. I'm not done yet. Now, the other thing we now have to do, so now we can go back and use our equation here. We got all the parts. The thing is, we also have to remember that when we are using R, liters, atmospheres over moles, Kelvin, we have to have everything in the right units. We got to have our volume in liters, our pressure in atmospheres, moles is always in moles, and our temperature in Kelvin. So we're going to have to do a little converting here because this is my pressure of hydrogen now that I want to put in here, but it's in millimeters of mercury. So I got to do another step here, and I got to take that 665.2 and say there's 760 millimeters of mercury in 1 atmosphere. And if I do that calculation, I get, well, you know what? And let me calculate it real quick. Second. I don't have the same, hold on. So 665.2 divided by 760 is 0.8753 atmospheres. Again, I'm carrying an extra sig fig with me. I'm going to zoom out just a little bit here. Not that much. So we can see more of the paper. Okay, so now that is my pressure of hydrogen in atmospheres, and I'm going to put it in this equation. So I'm going to use this here. So 0.8753 atmospheres, that's my pressure of hydrogen. Volume was my 7.80. Divided by R. There's my R. And divided by temperature. And that temperature was given up here as 22 degrees Celsius. 22 degrees Celsius. I got to convert that to Kelvin down here. And that is 295.15 Kelvin. I'm the sig fig on the 5. So Kelvin cancels, liters cancels, atmospheres cancels. I got 1 over moles. It'll come out in moles. If I do that in moles, let me see what I got here. One second. Yeah. So I get 0.2819 moles of hydrogen. Okay. Now I'm carrying extra sig figs with me. What I'm really doing is just leaving that in my calculator because I have another step. So although I wrote 0.2819, my calculator says 0.281876, blah, blah, blah. I'm keeping that in my, I'm going to use that next because the next thing is, remember the question wanted the mass. Need grams. So we got to go from moles to grams. One more step. Okay. So I would just normally just keep writing, but I'm writing big, so I ran out of space there. 0.2819 moles of hydrogen times 1 mole of hydrogen is 2.016 grams. Okay. So I'm going to take that number that's still in my calculator times 2.016, and that will give me 0.568 grams of hydrogen. Okay. And now, because I'm at the very end of the problem, I'm going to round to 3 sig figs. It's where I should be. Okay. So that's how you do these. It actually takes less time to do it than it does to explain it. Just know that what I'm doing here is on these collected over water problems is I have to always have this. It's actually, well, actually it's this. Collected over water. There's different ways to ask these. This is probably one of the simpler ways. There's different ways that this can be incorporated into a problem. Right now, I'm just saying it was collected over water, boom, what's the mass? This can be part of a stoichiometry problem where you say this reaction occurs and then the gas is collected over water. So this could be one part of a bigger stoichiometry problem that can be done. So watch out for those. So, but this is the key, is knowing that. Sig fig wise, some people get a little confused because they say, well, there was only 2 sig figs here. Why did I end with 3? Well, that's because when I added for the temperature, So that's how I'm getting the temperature into Kelvin. This is adding. So I don't count the sig figs in my temperature. I count the decimal places, because for adding, we count decimal places. Just like over here for subtracting, we counted decimal places. I carried an extra one there. Okay, I carried an extra, oops, that's not very good. 5. So I carried an extra one here. This is where my sig fig is. So over here, this is where my sig fig is going to be. But I brought it with, but I wrote it down here, and I wrote that little notation. To me, that's a line above or a line below the number. It's just my own little signal to tell me where my sig fig is. That's the end of that one. Your answer is 0.568. After this, the next topic is kinetic molecular theory, which is right here. And I already posted a video on this by someone else, and it just goes over these 5 postulates. So go ahead and watch that one. I will come back and I'll make another video on how to use this equation on the bottom of page 97, and we'll do some problems with that. So I'm trying to do some problem solving equations with you guys. All right, take care. Hope this all worked out. See you later.